we're out of time. So
You're going to look at it. All right, they're going to.
welcome everybody to today's camp colloquium. I'm very pleased that Elizabeth Paul is speaking today. So Elizabeth has been part of this collaboration on stellarator optimization that I've been part of for the past, I guess, past 4 years, but I think I first met her when we were still in the pre-planning phases for it. So I met her something like 5 years ago, and have been watching interesting stuff coming out from her for that entire time, at the intersection of sort of applied physics and plasma physics and a lot of applied math, PDE constrained optimization, adjoint methods for PDEs. And today she's going to be talking about some of that work and shape optimization for stellarators, and I will let her tell you all about it.
Well, thank you so much, David, for your invitation. So I'm going to start off by saying that I'm really not a mathematician. My training is in physics, so I'm going to do my best to explain the physics that I'm going to use at the outset and hopefully make this clear for you all and highlight the intersections of applied math with the impacts on the class of physics. So here's an outline of my talk. I'm going to start with a really broad introduction to what I mean by magnetic confinement and why we need to optimize the shapes of stellarators. I'll then talk about how I've used adjoint methods in my research for several applications, and then this will transition into my more recent work on energetic particle confinement and how I'm going to look toward the future. So we're interested in toroidal confinement for several reasons. So one of the main reasons is for nuclear fusion. So if we can confine the fusion fuel for sufficient densities and temperatures and confinement times, so we can get a self-sustaining fusion reaction and get a net energy gain from that. Toroidal confinement also has applications for non-neutral plasmas, which are relevant for astrophysical problems. There has been some work at Columbia University in this direction. Hot laboratory plasmas also have basic plasma applications, and stellarators have been used to confine electron-positron plasmas recently. So when we're thinking about toroidal confinement, we're taking advantage of the fact that if you have a strong magnetic field, the gyration of the charged particles gives you perpendicular confinement. So if you have a strong vertical magnetic field, then the charged particles are going to be confined in the perpendicular direction, so they're going to stay close to a given magnetic field line. And we call the averaged motion of this gyration the guiding center. So the guiding centers are going to be aligned with magnetic fields in this type of configuration. But the problem with just a straight magnetic field is that you can get the escape of particles out the ends. And so the naive approach would be to just close this into a torus. And now the slide will advance. Here we go. You can close these field lines into a torus to avoid the end losses. And so you would get gyro motion that gives you confinement of particles. So to lowest order, these guiding centers follow the field lines, and by putting them into a torus, you could avoid the end losses. And so this type of system looks something like the hybrid between an onion and a donut. So you want your magnetic field lines to lie on these continuously nested toroidal surfaces, and we call the direction the short way around the torus the polyoidal direction, and the long way around the torus the toroidal direction. So because guiding centers follow the magnetic field lines on average, the particles on average stay close to these surfaces and they stay confined. So you can build up a temperature gradient from this hot core to the cooler edge of your toroidal confinement device. So there's a problem because the particles don't actually stay tied to magnetic field lines. There's what we call a guiding center drift away from the magnetic field lines. And this happens whenever you have a curvature or a gradient in your magnetic field strength. And it's impossible to actually put your magnetic field in a toroidal configuration without building up such a curvature or a gradient in the field strength. The magnetic field is naturally going to be stronger on the inside of the torus than on the outside of the torus. And this gives rise to a drift in the B cross, grad B direction. So because the helices, this helical motion is going to give a gyro radius that is tighter, where the gradient, where the field strength is larger, this gives you a drift in the vertical direction. And the way to counteract this drift is to get field lines that go from the outside of the torus to the inside of the torus. So this samples the drift that takes you away from a given magnetic surface to a drift that gives you a drift back up to the magnetic surface. So the ideal situation is having a magnetic field line that goes from the outside to the inside of the torus, so that the particle always stays pretty close to a given magnetic surface. And so we need this net winding of the field lines around the torus, and we call this winding number the rotational transform, or we label it by the Greek symbol iota, and iota measures the number of poloidal turns of a field line per toroidal turn. So this is one of the necessary ingredients to get confinement in a torus, and the rotational transform can be generated by several different mechanisms. So in general, we can generate it by current. This is the most obvious way to generate rotational transform. So to do that, you have a strong current in the toroidal direction. So that's indicated by these red lines. By the right-hand rule, that gives you a poloidal direction of your magnetic field. And you get a toroidal direction of your magnetic field by some coils that look like this. And this is the mechanism that's used by the tokamak magnetic confinement concept. So the advantage of the tokamak is that you get a fairly simple setup. So all your coils can be exactly the same shape, and you get symmetry in the toroidal direction of your device. But there are some downsides to having to drive this current to give you the confinement, which I'll talk about a little bit later. And there are other ways to get this twisting of the field line, which may be a little bit surprising at first. The first way to get this without current is through rotating ellipticity. So if you look at the very core of your device, the fields, these surfaces collapse onto a single line, which we call the magnetic axis. And near this core of the device, the magnetic surfaces are elliptical in shape, which are pictured here. And so as you go around the device, the ellipticity of these surfaces begins to rotate, and that rotation gives you the twisting of the field lines, which gives you the rotational transform. And this mechanism is used in a stellarator called the Large Helical Device in Japan, which you can see pictured there. And there's another mechanism which is called torsion of the axis. So torsion is a measure of the non-planarity of a given curve. So we have this curve, the magnetic axis, that is enclosed by all of these nested surfaces. And if this curve doesn't lie in a plane, so it wanders in and out, it gives you some rotational transform. And this was the mechanism that was used by Lyman Spitzer, who invented the stellarator. Lyman Spitzer was the founder of the Princeton Plasma Physics Lab, where I now work. And here you can see a picture of him with the figure 8 stellarator. You can see it's very, very simple, so it's produced by circular coils. And you can see that the shape of the surfaces wanders in and out of the plane. And that gives you the net confinement. So historically, stellarators were one of the first magnetic confinement concepts to be built, but they didn't have initial success, and they were soon overcome by other confinement concepts. But they've recently had a resurgence, which I'll talk about. So I've mentioned that one of the ways to get confinement is by driving a current, and one of the advantages of this approach is because that it allows you to have a symmetry direction. So in a tokamak, you have a symmetry direction in the toroidal direction, and if we look at the Lagrangian for a single particle, this tells us that we get a corresponding conserved momentum. And we call this P5. And you can actually show that this toroidal momentum is going to give you the P5 that is approximately constant on these flux surfaces. So it tells you that on average particles are going to stay tied to these magnetic surfaces, and you essentially automatically get good particle confinement for any kind of device that you think of, as long as it's toroidally symmetric. So that's one of the main advantages. And now let me just lay out some of the the features of the tokamak. So a tokamak is a magnetic confinement device that has this toroidal symmetry, but it requires this strong toroidal current. And the advantage is that you get automatic particle confinement. The magnets are fairly simple. They're essentially planar curves that give you this magnetic field. However, it requires a very large current in the plasma, and this can be a driver for instabilities that can give you sudden loss of your confinement. And driving this current in steady state can be challenging and inefficient. So it generally requires some induction, and you can't increase the flux through this coil indefinitely, so it's challenging to do this in steady state. So the alternative to using current to get rotational transform is the stellarator. So the stellarator uses instead the 3D toroidal shaping to get you the rotational transform. So that's either through the rotating ellipticity or the torsion of the magnetic axis. And the problem is that because you no longer have this toroidal symmetry, you don't have a corresponding conserved momentum that gives you automatic confinement. And so we have to generally carefully optimize the magnetic field in order to get the confinement times that we would like. And in order to get this twisting of the field lines that gives us the rotational transform, it requires some rather complicated magnets that give us this rotating shape. So here you can see a schematic of the W7X stellarator in Germany. And the magnetic field is provided by these rather complicated coils in blue. The main advantage is that because we don't have to use current, you have low recirculating power. So in a fusion power plant, you wouldn't have to take some of the energy that's coming from your fusion reaction and put it back into driving the current in your device. So it's better from the economic point of view. And because you don't have current, you don't have a drive for potentially plasma terminating disruptions. So although there are some challenges, there are some clear advantages to looking at the stellarator again. So one of the really surprising features of a stellarator is that you can actually get something analogous to axisymmetry even when you break the continuous toroidal symmetry. And this has to do with looking at a modified Lagrangian and looking in the very strong magnetic field strength limit. So this gives you what we call the guiding center Lagrangian. We're just following the average motion of the charged particles about field lines. And you can show that this modified Lagrangian only varies on these surfaces through the magnitude of the magnetic field strength in some particular coordinate system. So this tells us if we have some ignorable coordinate in the magnetic field strength in this coordinate system, we get a corresponding conservation of momentum, analogous to what we would get in axisymmetry. And again, you can show that this P phi, this angular momentum, gives you particles that are confined to some magnetic surfaces. And we call this feature quasi-symmetry. It's a hidden symmetry. It's not obvious when you look at the field in three-dimensional space. And there are different flavors of this quasi-symmetry that we can see in practice. So we can get contours of the field strength that close in the polygonal direction, the short way around the torus. So here's an example of the QPS device that was devised at Oak Ridge National Laboratory. So if you take a look at this is the boundary of the plasma, you can see it's very clearly far from any kind of obvious symmetry. But only when you look at the field strength in this particular coordinate system is the symmetry become obvious. We can also have helically closed contours of the field strength. This is a device that's in Madison, Wisconsin, and this is currently the only existing quasi-symmetric device. And you can also get quasi-axisymmetry. So here this is most analogous to a tokamak, so you get contours of the field strength that close in the toroidal direction. But when you look at the device in three-dimensional space, there's no clear symmetry direction. So we've been able to demonstrate that quasi-symmetry exists in numerical calculations, and we've been able to see it in practice in the HSX device. Okay, so why do we need to optimize the shapes of stellarators? So the main reason for optimizing the shapes of stellarators is to get properties like quasi-symmetry or particle confinement. If we look at a general three-dimensional field, we don't have any conserved momentum. And so we have to very carefully optimize the field in order to get this property. And typically we do this through numerical optimization. So we need the magnetic field to satisfy the MHD equilibrium equations. So the MHD is a model that combines Maxwell's equations with a fluid model of the plasma. And so we provide the shape of some boundary of a device, like this one that is shown in green. And the equilibrium equation tells us what the corresponding magnetic field is everywhere in the volume. And so once we know what this magnetic field is, we can compute different figures of merit, for example, a quasi-symmetry or some measure of the confinement time. And so the goal is to optimize over the shapes of the possible plasma boundaries, find the optimal one that will give us very good confinement. And then as a second step, we have to actually find the magnets that will give us this magnetic field. And this can be formulated as an inverse problem. So we want the field that's normal to this desired surface to be close to zero. And this will have some component that comes from the plasma itself and some that comes from some external magnets. And that can be computed from the Busev-Art law. And so this gives us another optimization problem that couples the desire for producing this field with some measure of how complex these coils are. So we have to take into account that we can't build any coil set that we would like, but we have to account for, is it actually possible to engineer these things in practice? And this is what we call a two-stage optimization approach. So stage one, we find this target boundary, and stage two, we find the magnets. So we now have evidence that this two-stage approach actually works. And the best evidence for this is the W7X device that I mentioned earlier. It was designed in the 90s, but it just came online in 2015. And they've now been able to actually demonstrate the reduction in the transport that is associated with the optimization of the magnetic field. So in these studies, what they did is they measured the actual heat flux in the experiment, and they normalized it by what they calculate from a collisional transport theory. And in the real device, which is shown here at the bottom, you can see a number that is less than 1. This tells us that there's some other measure of transport in the experiment, which has to do with turbulence that you can't really optimize away yet. And if you try to perform the same calculation in a different device that was not optimized, such as LHD, you get a number which is much greater than 1. So this tells us that if we did not carefully optimize the magnetic fields in W7X, you couldn't support the same temperatures and density gradients. So this is evidence that all the hard work that goes into the design of these magnets is paying off in order to get record-breaking confinement times. So we have evidence now that stellarator optimization works, but there's a lot of challenges that remain. So one of the challenges is that we have to navigate this high-dimensional space that describes complicated geometries. And so this can be taxing numerically. And the other challenge is the possibility of very tight tolerances on the positioning of coils. So physical parameters can vary very sensitively on the parameters of the coils. And this can give rise to very tight tolerances, which can increase the cost of your device. And we can tackle both of these challenges if we know what the derivatives are. So if we can calculate how sensitive a given physical parameter is with respect to perturbations of the coil or the surface shape, then we can try to address both of these challenges. So a lot of the work that I've done is taking advantage of advances that have been made in other fields and bringing it to the plasma community. And one of these advances is in the notion of the shape gradient, which tells us something about the local sensitivity of a figure of merit to a perturbation of the shape. So in these figures, you can see an example of the shape gradient for the drag on this car. And so this tells us if we were to push the car inward in the red region and outward in the blue region, we could reduce the drag on the car. And the shape gradient is defined in this other box as this script G parameter. So this is a surface integral over the shape of the car, for example. And so it tells us a measure of the local sensitivity to the drag. And we can actually get the shape gradient very efficiently by using adjoint methods. So adjoint methods allow us to compute the sensitivity without actually directly perturbing the shape many times, but by defining a corresponding adjoint equation, which I'll define soon. So we've been able to apply this approach to the stellarator problem. So here's an example of what the shape gradient looks like for the rotational transform of a stellarator. So you could figure out how to move in this very high dimensional space that defines the stellarator. So the derivatives with respect to shapes can be defined. So we can think about some underlying shape in green that we're perturbing with some velocity field delta x to give us some perturbed shape s script epsilon. And then the shape derivative can be defined in a similar way that we see for functional derivatives. And we have the Hadamard-Celesio structure theorem that tells us that the shape derivative of a given function can generally be written in the form of the shape gradient. So if we know what the shape gradient is, that essentially tells us all the derivative information that we need to know about our figure of merit. So for some figures of merit, you can just write down what the shape gradient is. So for example, if you want to know the shape gradient of the volume, you can actually derive that as 1. But for a lot of figures of merit, it's much more complicated. So for the problems that we're interested in for the stellarator, our figure of merit actually depends on the solution to some PDE. And so you can't just write down what the shape gradient is, and we have to go to the adjoint method to figure out what our shape gradient is. So what do I mean by an adjoint method? So I'm thinking about a problem where we want to constrain a PDE to be satisfied. So I'm saying my PDE is L is equal to 0. So L depends on omega, which are some set of parameters defining our optimization space, and U, which is our solution or our state variable. And we can write this in a weak form by integrating against some test function Q. And so we want to essentially minimize this objective function with respect to our set of parameters. So our objective function can depend directly on our parameters omega and indirectly through the state variable U. So we can enforce this PDE constraint by using a Lagrange multiplier. So we define our Lagrangian, which depends on our parameters omega, our state variable U, and this Lagrange multiplier. So our Lagrangian is our objective function plus this constraint term. And then we can define our adjoint problem. So our adjoint problem is setting the derivative of L with respect to the state variable equal to 0. And this gives us some linear equation for this Lagrange multiplier Q. So with this clever choice of the Lagrange multiplier, then the derivative of our objective function becomes much simpler. So we can compute the variation of this cost function, and you can show that it's actually equal to the variation of the Lagrangian, because this constraint is satisfied when we're computing the derivative. And the derivative of the Lagrangian generally has two terms, corresponding to the explicit dependence on the parameters and the implicit dependence through U. But because we've chosen our Q to satisfy this adjoint equation, the second constraint is, the second term is identically 0. So we're just left with the explicit dependence on our parameters, which is a rather simple expression that you can just write down. So at the end of the day, what this means is that we can solve two PDEs. So we solve this original PDE, L is equal to 0. And then we solve this linearized problem for Q, where delta L is equal to 0. And with those two PDE solutions, we can get all the sensitivity information with respect to any perturbation of our system. So while typically you would have to perturb with respect to every parameter that describes your boundary or your coils, which could be hundreds of parameters, you can instead get all the sensitivity just through these two PDE solves. So that's really the win that you get out of the Adjoint method. And you get a lot of bang for your buck if you're doing stellarator optimization, because we have this high dimensional space. So we've put this into practice for several problems of interest for the stellarator. So the first is for this MHD problem that I talked about before. So this is the first stage of that two-stage approach where we want to find the optimal shape of our plasma that satisfies the MHD equilibrium problem. And we want to think of some objective function that depends on this MHD problem through the magnetic field. So you can see this is it's a nonlinear PDE because you have this curl of B cross B, and we specify some pressure profile here, which depends on the unknown flux. So essentially this, the shape that we're specifying takes the place of our boundary condition. So we want to evaluate the derivative of our objective function with respect to some perturbation of our boundary. And so the naive way of doing that would be to just linearize the MHD equations for some specified perturbation to the boundary. And you can use some tools from MHD stability theory to write this in a convenient form. So we can linearize the MHD equations with respect to this virtual displacement C, and you can write the perturbations to the field and the pressure in a familiar form for MHD theory. But the problem with this representation is it requires solving a linearized problem for every possible perturbation to the boundary. So we want to avoid doing that by instead specifying an adjoint problem. So for the adjoint problem, we want to instead first solve the equilibrium. So curl of B cross B minus mu naught grad P is equal to 0. And then enforce the MHD equilibrium throughout the optimization using a Lagrange multiplier. So when we define this Lagrange multiplier, we have to choose some inner product to integrate with respect to. And for this problem, we can choose an inner product that is particularly convenient because the MHD force operator is self-adjoint with respect to it. So by using some physical insight, we can determine what is the most convenient way to enforce the constraint. So this convenient inner product is just an integral over the plasma volume. So that gives us our adjoint equations. So the adjoint equations generally take this form. So we have a linearized force operator, some inhomogeneous term, and then a boundary condition with no displacement. And then we can compute the shape derivative of F without ever having to directly perturb the plasma boundary. So we first know that the derivative of F is equal to the derivative of the Lagrangian. And we can write this derivative in a simple form that is just the integral over the plasma boundary with the normal component of the displacement. And if you remember, this quantity in parentheses is our shape gradient. So essentially, we've defined an adjoint method that gives us our shape gradient with only two PDE solves. So we have to solve this unperturbed forward problem, which is the original equilibrium problem, and then this corresponding adjoint problem, which is a linearized problem. And using those two PDE solves, we get the shape gradient, which tells us the local sensitivity of our figure of merit, or the perturbation of our figure of merit with respect to any possible perturbation of the boundary. So this shape gradient contains all the sensitivity information we need. So we put this into practice. This is the same figure I showed in the introduction to my talk. This is the shape gradient for the rotational transform and its deviation with respect to some target function. So the adjoint problem corresponds to f of c is equal to 0, no displacement of the boundary, and we simply impose some perturbation to the toroidal current profile. So we can actually use the same solver for both the forward problem and the adjoint problem because the problems look very analogous to each other. So we've used this within an optimization algorithm. So here we're using VFGS to try to push the rotational transform, which initially looks like this red function here, toward a target function which is essentially flat with respect to radius. So we start with this initial boundary on the left, which is a simple rotating ellipse boundary. And if we look at the Poincare plot of the magnetic field, you can see that there's a small island chain that we'd like to eliminate. Island chains are generally bad for confinement because you can get flattening of the pressure there. And by going to this case with very flat rotational transform, we can try to eliminate this island chain. And we get to this configuration on the right in blue, which has the target rotational transform, and we've eliminated this island chain if we look at the point gray section. So for the next application, I'm going to be talking about optimization for quasi-symmetry. So for the MHD problem, there's some limitations on what kind of functions that we can look at just because of the potential singularities that can arise in the MHD equations. And so for the quasi-symmetry problem, we've looked at some simpler models of the system. This is work that I've done with a student at Princeton, Richard. And instead of solving the full nonlinear MHD equations, we're just solving the vacuum problem. So in a vacuum, you can write the magnetic field as the gradient of a scalar potential. And we've relaxed some assumptions that can lead to some problems with ideal MHD. And so we want to essentially be able to quantify quasi-symmetry on one surface in our domain. And so we solve for the vacuum field PDEs, which is essentially Laplace's equation, in a toroidal domain with a Neumann boundary condition. And then once we know what the magnetic field is within this toroidal domain, we look at the field on the boundary and look at the straight field line coordinates, essentially. So we solve this additional ODE that tells us how the field lines twist on the boundary of the plasma. And this also gives us information about the quasi-symmetry. So our objective function takes this form here. So we want to optimize for quasi-symmetry. We want to get some target twisting of the field lines or rotational transform. And we generally have to fix the aspect ratio of our device because the optimizer can go to solutions with very large aspect ratio that are quasi-symmetric, but they're not exactly practical devices. So here's an example of optimization with this metric. So we've been able to achieve very good levels of quasi-symmetry on the boundary of our device. So on the top left, this is a plot of the quasi-symmetry error as a function of the radius. So you can see at the edge of the device where we're actually targeting the quasi-symmetry, we are able to do very well. And one of the features of quasi-symmetry that we can look at is how straight the contours are in this coordinate system. So if we had perfect quasi-symmetry, the contours of the field strength would be exactly straight lines, and by eye, that's what they look like. So we're doing fairly well. And we tend to find that the rotational transform gives us very flat shear. So it's a flat function of the radius. And these type of solutions that have very good quasi-symmetry on the boundary of the device is something that has been predicted by analytic theory, and we can now confirm with our calculations. So one of the reasons why having very precise quasi-symmetry is important is because it allows us to get confinement of the most energetic particles in our device. So now I'll go into the applications of these new configurations and some work that we're going to do in the future in this direction. So one of the reasons that people have been traditionally scared away from the stellarator as a magnetic confinement device is that they have historically performed poorly with respect to the confinement of the fusion products. So in a fusion reactor, you have a very energetic alpha particle that's created, and you want that alpha particle to deposit its energy with the background so that you can have a self-sustaining reaction. If you lose all those particles very early, then you can lose your source of heating, and you can also deposit heat in the walls of your device, and this can lead to degradation of your material structure, and you may have to replace your walls more often, for example. And so this is a really critical problem if we want to think toward a reactor. So there's been some efforts to try to minimize energetic particle transport in stellarators. So there was a reactor study out of Princeton. They produced this Aries CS stellarator power plant structure. And part of the efforts of this design were to minimize the transport of energetic particles. Even with this optimization, they found that they had very localized losses on the walls that could lead to increased heating and may be unacceptable. So it's important to revisit this problem and see if we can attack it with better numerical techniques. So here's a visualization of the statement I made earlier about the relatively poor performance of stellarators historically. So in this plot, this is showing the fraction of the alpha particle energy that is lost before thermalization. And a set of configurations that are stellarator designs we have at a computer that are all scaled to the same size and field strength. And you can see that these configurations can lose tens of percent of the energy before they thermalize. And this may be unacceptable. This includes the W7X device that I was showing earlier, and other devices that have not been actually constructed. So one of the ways to address this problem is to try to get very close to quasi-symmetry. So if we know if we have exact quasi-symmetry, we have the exact conservation of a momentum, and this conservation of a momentum gives us the confinement we would like in a stellarator. So in some of these historical designs that have been designed to get close to quasi-symmetry, you can see that the level of quasi-symmetry was not perfect. So these plots show the contours of the field strength on the boundary of the device. So again, in perfect quasi-symmetry, they would be straight lines. But in reality, you can see that there are some visual errors. And you can quantify this more exactly. So on the y-axis, this is some measure of the quasi-symmetry error as a function of radius. And it's something on the order of 10 to the minus 3 in these historical devices. More recently, because of advances that have been made in the optimization, we found some new configurations that have much better position of quasi-symmetry. So in the adjoint result I showed a few slides ago, that was just optimizing for one point on the boundary, but these can get quasi-symmetry over the whole volume. And it's orders of magnitude better than has been ever produced before. So we call these precise quasi-axis symmetry and precise helical symmetry. And if we look at the field strength contours, again, they're very straight by eye. So we now have the capability to produce these configurations with very precise levels of quasi-symmetry, not just at one surface, but even throughout the whole volume. So these configurations, although they have precise quasi-symmetry throughout the volume, they can take significant CPU hours to produce because derivatives are not available. So for the adjoint configuration, we do very well on this one surface, and it's the type of calculation you can do on your laptop very efficiently. And we could use this method to kind of scan out the parameter space and find regions where we could have better quasi-symmetry, and then polish it off again with methods that don't have derivatives, and they take more CPU hours to obtain. So with the combination of these two methods, we can find configurations with enhanced quasi-symmetry. And the real reason why it's important to look at these configurations is we can improve the energetic particle confinement. So this is the same plot I showed a few slides ago. So in addition to the historical configurations, we found just within the past year a bunch of configurations that have losses that are analogous to that in the tokamak. So the last configuration you see on this plot is ITER without coil ripple. So ITER is a very large tokamak that's being built in France, so it is axisymmetric. And even in that configuration, you have a few percent of losses. And you can now find stellarator configurations that have losses that are at the same level or even lower than in tokamak. So this is really a step forward for the stellarator. I'll emphasize that these configurations have not actually been built. These are calculations, but it at least demonstrates that it may be possible to have a stellarator that sufficiently confines the alpha particles. Okay, so now we'll come to the conclusions and outlook. So there's a lot of complexity that we don't take into account in the models of our energetic particles. So in the plot that I showed on the previous slide, we're simply initializing a bunch of Monte Carlo samples of the particles, following their trajectories over time and looking at how they're lost. But in reality, there's a lot of physics that's hidden behind those calculations that we could perhaps look at more rigorously. So there's a lot of ties between the guiding center dynamics and nonlinear dynamics. So for example, we can, instead of looking through all of the trajectories themselves, we can look at a point gray section, which quantifies the resonancy, the possible resonances in our system, and how islands may overlap and lead to chaos in the dynamics. And in addition, the particles can interact with perturbations that arise in the background itself. So there are certain natural waves that arise in a plasma, such as alphane modes. And the frequencies of these modes can resonate with the particle dynamics and lead to enhanced transport. This is a phenomena that's been measured in many tokamaks, for example, in recent jet discharges. And now that we can demonstrate that stellarators have reduced confinement without accounting for these effects, we now need to go back and take a closer look at the physics and see how the guiding centers interact with possible perturbations. So if you have a periodic device like a stellarator, you can get physics that is analogous to band gaps. So because you have a continuous spectrum in the alphane modes in a periodic medium, these continuous modes can couple to each other through the geometry, giving rise to band gaps. And we can have a global eigenfunction that can sit in the band gap, and this is the mode that can feed back on the particles and give rise to enhanced transport. So I'm interested in building up the tools and the frameworks to model both the nonlinear dynamics of the particles, but also the MHD activity and accounting for how the particles feed back on the MHD activity. I'll also mention that I'm moving to Columbia in January, and I'm interested in putting into practice some of the optimization that I've developed in a new experiment. So at Columbia, there was a very simple stellarator that was built in the basement that looks like this, called the CNT stellarator. And it was designed to confine non-neutral plasmas, such as air plasmas. And you can see that it's produced by these simple circular interlocking coils. And it gives rise to this large aspect ratio torus. So because this was designed for non-neutral plasmas, which have a large electric field that gives confinement, it's not really applicable to the neutral plasmas we're interested in. And so we instead want to get all the confinement from the magnetic field and re-optimize the coils to give enhanced confinement. We also want to use this as a test bed for new technology, such as high-temperature superconductors to build the coils. So we're going to 3D print essentially a track for this HTS tape to sit on and give us the magnetic fields. And we want to keep the simplicity of the coils to give us good access. I also want to mention that I've made an effort with some collaborators to put together an introductory text to make the stellarator literature more accessible to people who are outside the field, such as people from applied mathematics. So we have a version of this text that is available on the archive. So if you're interested in reading more about what is a stellarator and how your math may contribute, I would welcome you to take a look at this. So we really try to start from first principles like Maxwell's equations and classical mechanics and build our way up to the optimization problem itself. And yeah. So now I've come to my concluding slide. So the main advantage of stellarators is we don't need a large plasma current to give us confinement. And this is better for the economics because we don't have to take energy from the fusion reaction and put it back into driving the current. And we have less drive for instabilities in the plasma. And the real surprising thing is, although we break this toroidal symmetry, we can get this hidden quasi-symmetry that gives us integrability of our particle trajectories because of the p-phi conservation. But we need numerical optimization to find this. And adjoint methods have allowed us to more efficiently and accurately compute derivatives for gradient-based optimization applications, and also for looking at sensitivity. And a lot of the previous challenges for the stellarator have now been addressed through numerical optimization. And this is demonstrated in the excellent confinement in new configurations with very good alpha confinement. And so the coming years, my research will be focused on further developing the numerical methods and the optimization tools for stellarators, finding new configurations for the on-campus experiment, and then modeling the complex dynamics of fast ions in these 3D configurations. So thank you for your attention.
We have time for questions. John.
Do you take the shape of the accelerator into account in the coordinates that you use in order to parameterize it?
Yeah, so when we're describing these shapes, it's typically in Fourier space. So for example, you may say I want R and Z, the cylindrical coordinates, to be Fourier series and the two angles. And so we use Fourier series because it's a toroidal shape. But otherwise, we don't really use the shape as in
So
defining
things like the
coordinates.
curvature aren't really taken into account in parametrization.
Not really, yeah.
Would it help to do that?
So you said using the curvature,
Curvature.
like the surface curvatures, the principal curvatures?
Yeah.
It's possible. Yeah, I'm not sure how you would exactly use the curvatures to define a parameterization, but it's possible you could. I'm not sure.
In your CNT project, I know like the previous version when they designed it, they did some sort of like design based off perturbation. So it was like super robust, the engineering errors. Did you guys also think about this in like the upgrade you're making, or is that taken into account somehow?
That's a great question. I think, I mean, this is work that hasn't really started yet, so I put some initial picture, which
Okay.
is just a schematic of some initial attempts to find. So it looks like you can find these configurations, but there hasn't really been any, a lot of effort toward the design. But yes, I think it would be important to find a robust minimum, because this is something we want to be able to build on campus with basically graduate students finding the tapes themselves. So we want to leave a lot of room for error if possible. Yeah. But
Adding on that shape parameterization, why weren't like splines used? I think a lot of times, like for like in aviation, they use like nodes and splines for shape optimization.
yeah, that's something that has been started to be used for the coil problem. So you have like a closed curve that defines the coil, and that has been used, been described by splines. But yeah, we haven't built up the infrastructure yet to do that for these surfaces, but I think it could be useful. Yeah, I agree. The Fourier series method doesn't always converge very well because we're basing everything off of cylindrical coordinates. If you have these shapes that vary very strongly from a circle, then the Fourier series doesn't work as well. So yeah, I think splines would work well, but we haven't actually moved in that direction.
And you alluded to these challenges of working with sort of tolerances and other engineering constraints. Do those constraints kind of go into the optimization problem itself, or is that something you just sort of evaluate after the fact to see if something is workable?
Yeah, so for the tolerances, there's been some effort to take that into account in the optimization by trying to find minima that are broad and flat rather than just peaked minima. And so you can use robust optimization techniques to try to build that into the problem. And yeah, whenever we're building coils, you have to take into account their complexity to some extent, because the problem is really ill-posed. There are many possible magnets that can give you the same magnetic field. And so the optimizer will generally try to find a solution that is very complex and something that's not buildable. And so we have to take into account the curvature of the coils, how close they are to each other. So you want sufficient space between the coils to allow for things like diagnostics and ports. And you sometimes have to look at the forces on the coils, make sure they're not too strong because you have to support them. Yeah, so this is something that definitely has to be taken into account on the physics side.
Similarly, with the energetic particles, you were saying that you make this as absolutely quasi-symmetric as possible, so you can achieve there. But are there other factors that maybe you're developing these factors that you come into the or terms in your target function?
Yeah, so for the quasi-symmetry problem, these were all, so you take into account quasi-symmetry, aspect ratio, rotational transform. So it's a very simple problem. It's the minimum problem you need to find an interesting configuration. But it's not the minimum physics that you need to have an interesting device. I would say the next important piece is having something that is stable. Okay, so we know you can have an equilibrium that has this quasi-symmetry, but if you actually build it, it may have some huge instability so it doesn't stay there very long. And so that's not that interesting. So I think the next piece is building in the other physics we want in addition to quasi-symmetry. And we may need to relax away from quasi-symmetry in order to do that. So we know that having a conserved momentum is not required to get good particle confinement. There may be other ways to do it. And so I think directly looking at the particle confinement without quasi-symmetry may be an interesting direction.
Touching on that, we've been shooting for as good quasi-symmetry as we can get, and usually using some type of L2 norm measure for the quasi-symmetry or deviation of quasi-symmetry. But it's never been clear to me to what extent, what is the relationship between close to quasi-symmetry and close to confined? Like, it's.
Yeah.
I understand it qualitatively, but do we have any quantitative measurements for that?
I think I've seen some results. It tends to be a very sharp function. So as you get really close to quasi-symmetry, the confinement just drops down, depending on how you look. But the errors, like different types of error deviations from quasi-symmetry have different impacts on confinement. Like if you have a resonant perturbation that resonates with a particle frequency, then that's going to have a much larger impact. And so I think being aware of the dynamics of the system is going to be helpful to diagnose what kind of quasi-symmetry errors we can tolerate. Yeah.
So does this imply that we should be thinking about measures other than sort of an L2 error or something that's weighted so that
Yeah.
applies more against some of these things that you know are going to be dangerous?
I think that's important. So another feature to look at is the formation of local wells along a field line. So that can lead to local trapping and different types of dynamics. So if you can be aware of what type of dynamics you need to avoid, or what type of dynamics is there in your configuration, that's something you can try to penalize directly, then rather just be dealt with too far. Yeah, I agree.
Question?
Yeah.
One of the benefits of local losses, though, is for diverters if you need to dump alpha particles in a real fusion reactor. So are you trying to take such practical considerations into account as well?
Yeah, I mean, that's another strategy for the alpha problem, is to kind of accept that there are going to be these losses and to instead try to localize the losses on the ball. And so they may not be in the diverter structure that you built, but you could maybe build a secondary diverter, like put a little bit of liquid metal on the wall where you know the losses are going to come out, and just to use that strategy to try to prevent the localized heating on the structures. So yeah, I think it would be important to study how sensitive the losses are to perturbations. If you know that the losses are always going to come out in a certain place, then you could design a structure to intercept that. But if not, then maybe that won't be a good strategy.
Okay, seeing no further questions, and we thank you. Let's thank Elizabeth again. And
We're not in a hurry on the kinetic vector or something. We're not, do your exam first.
Yeah, I do want to, but I mean, I have like stuff that
Yeah, so like, I mean, currently, what I have. I know, and Max seems like a change in his main. So.
Okay, how are you doing?
Great.